Our next speaker is Professor Dan Steingart. Dan is an assistant professor with a joint appointment in mechanical and aerospace engineering and the Andlinger Center for Energy and Environment. Dan is by training a material scientist and engineer. He got his undergraduate degree at Brown and his PhD at UC Berkeley. He is working at the interface between material science, material systems, and shortcomings in electrochemical systems. Dan has been at the City College of New York before joining Princeton, and prior to that he has been working in a startup, internet-type company. His work has resulted in several startups. I understand 5 of them are still viable, which is a usually high success rate. And Dan is going to talk to us right now about his work on battery and shortcomings of batteries.
Thank you. Viable, not profitable. So important difference. But still going. Thanks very much, Peter and Emily, for a fantastic introduction to the wonderful things that are happening at Andlinger. Thank you, Maury. And thank you, everyone, for giving me your time this morning. As Peter mentioned, I came to Princeton a little over 3 years ago, and people said, why are you coming to Princeton? And I said, to think about batteries harder. So the idea is how do we look at what the limitations of what a battery is and what are the unexplored things within what a battery is. This is why I call the talk Hidden in Plain Sight, and improve is in quotes, because I think improving batteries is a balance, and it depends on what you want. So I just want to give kudos in advance to my students who sort of went to war on problems that are off the beaten track, and I really want to thank Ellen and ARPA-E for being quite generous with funding to allow me to tackle some of these problems, as well as direct funding from Andlinger and CMI, as well as some corporate partners, Israeli Chemical Limited, Xerox, and recently Alpha N. So when people ask me what I do, I say I'm a battery person. They say, well, does that mean you're a materials chemist or a materials scientist or chemical engineer? I say, no, I'm a battery person. And they push me and they say, okay, well, I think about electrochemical reactors. And recently we see a lot of innovation directly related to battery materials, and yes, they're very, very important, but batteries are reactors, right? So in a reactor, we put energy in and mass comes out, and depending on what we want to do, we either create mass or well, we never create or destroy mass, but mass goes in, it stays in, or it comes out. Energy, in the case of a battery, comes in and comes out. And when we think about reactor design, typically we want that reactor to go one way. Right? But when we have a battery, and particularly a rechargeable system, we want the battery to store energy and then release energy, right? So it's inherently a suboptimal problem as far as chemical engineers are concerned. And I only realized this when I taught in chemical engineering for 4 years. That was an exceptional experience. So I'm going to talk about closed systems and the funny things that come out of closed batteries when you think about it this way and you abstract a little bit from the materials. And this is what a battery looks like. It has an anode, it has a cathode, it has 2 current collectors and an electrolyte. And this is sort of the rote vision of what we consider a battery, and it's become an implicit compromise. When we think about a closed battery, it has to look this way. But what is in that compromise, and what can we reconsider? So batteries have always been a negotiation, and I think one of the most important papers on the negotiation was written as a master's thesis, a professor of mine at Berkeley, John Newman, and it's this idea that you have to trade between energy and power. So we'd like to think of energy as something that you can put in a bucket and pour in and out, and then if I just put water in a bucket, then what determines how fast the water can come out? Well, gravity. So why can't I empty a battery as fast as I empty a bucket? And this paper really put the first quantitative framework analytically to this problem in a direct way. And then over the next 30, 40 years, his group pushed it to cover an entire battery. So out of this, we get something called a Ragone diagram. And a Ragone diagram is a fancy word for something, or fancy name for something that shows how energy and power are related in a battery. And what we see in this diagram is that for a given chemistry, same materials, depending on how I put the materials in that battery, I can optimize between energy and power. And the compromise comes down to something that's really, well, seems like a stupid analogy, but I think it's dead on. You have two parking lots. You have a parking lot that's your long-term storage, and it's cheap, and per unit area of that parking lot, you can store as many cars as you want, but it's going to take forever to get your car out of that, on average. Meanwhile, you have this parking lot down here that's optimized for power density. All of this space could be used to store cars, but because it's not, the cars can come in and out quickly. So inherently, in the way we put the materials within a battery, we're choosing between energy and power. And the math behind this is some complicated differential equations, but this is a pretty nice picture. But let's say somehow we break this paradigm. Someone really goes after it, and we come up with ways of literally transporting, some massively long quantum tunneling, I don't know, ions out of the structure, right? Star Trek stuff. What I've been able to think about since coming to Princeton is like, well, you've created another problem, right? So now let's say I have, so this is the Ragone plot of looking at many different chemistries overlaid. And the fatness of the bands and the size of the bands relates to different configurations. Those areas are not a mistake. Notice that the internal combustion engine is up and to the right. And this is when you do battery research, you're trained to do this as a graduate student, you want to go up to the right, you want to go up to the right. So we want to go up to the right so we can compete with an internal combustion engine. Thinking about internal combustion engines on a fixed energy power basis is silly, but we do it anyway because we like to make ourselves miserable. So what happens when I have a battery that hits that corner? What have I created? If I have something where I have double the energy density and 10 times the power density, right? What do we call this? We call it a bomb, right? So if I let this battery go, no matter what's in that battery, basic thermodynamics tells me that if I have a lot more energy over a smaller mass, then the temperature locally will go up enormously. And yes, I can make that battery out of materials that are inflammable. But even so, if something gets really hot, it's unsafe. If it gets really hot quickly, it's inherently unsafe. So we have to think about this. We have to be careful in what we engineer for, because people are going hard after the Ragone diagram. But when you look at when electric vehicles have been successful, they've gone the other way on the Ragone diagram. They've derated energy at the cell level. So working with Rob through a distillate, I was able to put together this framework that's quite depressing, but has given us room to explore, and I call it the unfortunate tetrahedron. So what we've optimized is between energy and power density over the past 50 years, or really 200 years, 50 years quantitatively. But now we want cheap grid-scale batteries. So let's look at capital cost and operating cost. And we don't have the nice quantitative solutions yet that describe the couple between operating cost and capital cost. And what we're doing in my group is trying to come up with ways of putting better math to this, at first in an Edisonian empirical manner, and then seeing what equations might come out of this. So what I'll argue is that Tolstoy was really an electrochemist. And Anna Karenina was his treatise on batteries, right? And the first line off the bat, all happy families are alike, each unhappy family is unhappy in its own way. And this describes battery in academia perfectly. We pick our poison, and then we try to make that system the happiest that we can, right? There is no system that does everything perfectly. And that comes to the second line. If you look for perfection, you'll never be content. Because even looking at the basic analysis I showed you for the Ragone diagram versus safety, you can't have it all. You're just not allowed, and you have to figure out how to deal with it. And finally, and then you really have to apply this to the stuff I'm going to show you when I get into the meat of my talk, anything is better than lies and deceit. It is so easy to pick your metrics and emphasize them, but I think it's important to show everything. I just got in trouble for showing a bit too much in a publication, but let me tell you why. So We have this concept for grid-scale batteries, and it has a silly title, I think you'll understand by the end of the section, that we want to make a battery that lives forever by dying every day. And it's antithetical to the way we've made batteries for the past 50 years, and it's a design study. And I just want to be forthright about this. It's a crummy battery based on traditional metrics. But on the metrics, right, it's not the hero we want, it's the hero we need, maybe. So what do we need? We need something that's dirt cheap. So battery costs are difficult. I think the best way to consider the cost of a battery is to look at how much the capital cost is and then how many times you can use it. And when you take the first number and you divide it by the second, you get a number that looks awfully similar to the number that's on your PSE&G bill or Con Ed bill. And this is just the bucket for storing energy. And what that number tells you is that every time you use that battery, that's the price you pay. So if we want electricity to be anywhere around what it costs today, I think it has to be under 10 cents per kilowatt hour. And this is what my group has been working on for a while now. And there are two general approaches to this. Tesla is grinding on this too, and everyone working on lithium-ion batteries are grinding on this as well. And there's two approaches to this. You take lithium-ion batteries, which has been optimized wonderfully for this balance between energy and power. And then you climb, right, and now I'm biasing you with the directions on my diagram here. You bias it so you're going uphill to try to take this thing that you've optimized for energy and power and make it simultaneously cheaper. What I'm saying is that let's start with the cheapest battery that exists, my favorite battery, alkaline AA cell, and then add more cost to make it cycle. So why does a AA battery die? Why does any battery die? So there are three ways to die, gross estimate. You have corrosion, you have passivation, and you have too few or too many connections, right? And that last one is annoying, as Chief Wiggum said on The Simpsons. If your nose is bleeding, it's because you picked it too much or not enough. So the question becomes is what does this mean? And this is a battery I designed at CCNY, or helped design. And I wanted to point out that it short circuits. So it short circuits as a matter of operation. So we didn't want it to short circuit when we designed it. But what you see is a zinc anode, a zinc negative electrode growing into and touching a positive electrode. And you see that the zinc deforms when it hits that electrode. Nothing blows up, no graduate students or postdocs die. The battery continues to operate. We continue to cycle it. So we realized that short circuits are a nuisance, but not necessarily an anathema. So we could design a battery that could short circuit and you can recover from it. And some colleagues of mine, when I left Princeton, they left CUNY and formed this company. When I left, I'm sorry, CCNY, I hope I don't leave Princeton. And they went and formed this company, Urban Electric Power, that's trying to commercialize this. But it's still too expensive because it might last forever, but you're not going to get to a number where you can amortize, get enough cycles. There's just not enough days to make it cheap enough in a relatively small time scale. So we had this thought experiment. Why was this battery so expensive? We're using very cheap things and we were letting it do whatever it wants to do, but we had all of this support structure around it that cost money. So when you have to make batteries to the grid, everything counts. So this is this thought experiment that says, how do I get rid of this normal support structure? And the idea is that we have a battery that has a minimum number of stuff beyond the core components of the electrochemical reaction, and we give up energy density and we give up power density, but we also give up things that we haven't had to give up for 30, 40 years, like round-trip efficiency and self-discharge. Right, so this is a battery that fails on many modern metrics, but as you see in this video, so this is it charging, and this is it discharging, and it's a density-separated battery, and we're working with the physical chemistry, not against the physical chemistry. But the point is that it's short-circuiting all the time, and it is self-discharging all the time, but it never dies. It never dies in the traditional sense. That is, the battery, the standard death mechanisms just reset the battery and gives you a do-over and says, let's try again. And you can reform the battery electrochemically. So picking certain numbers and really not going after energy density, but going after cost and going after cycle life we've been able to find a cycling regime that at relatively low power competes pretty well with flow batteries. The diagram on the right shows that if we push it too hard, we have very, very bad round trip efficiency. But if we don't push it too hard and we can design it for a 4-hour cycle, it might be okay. There's a ton of room for improvement. It's a pretty crummy battery. And just to show you, when it operates really badly, it short circuits and just recovers. Right, so anything is better than lies in deceit. You have to tell, right, with a big grain of salt, right, this battery has really bad self-discharge. So it can make doing arbitrage difficult. But if the battery costs 1 cent per cycle, it might not matter. The battery has really poor power density, which means that it has to be dirt cheap, $50 per kilowatt hour or cheaper. This battery uses uncomplex bromine, which can be a safety issue, and we're trying to figure out why uncomplex bromine is unsafe if you can cap it in a certain way. Moving uncomplex bromine around is really unsafe. But if it's in a fixed vessel, it might not be so bad. So this battery has 3 ways to die. The really 3 ways to reset. So the corrosion returns the battery to the discharge state. We've engineered out all of the passivation reactions, and the too few, too many connections simply reset themselves. We pay for it in losing round trip efficiency. And we think that if we can prove that you can push this out, and really time will only tell. Thus far, we've been running these batteries, and you can see them in my lab running for over a year, and they've been running as if they were day one. So they're horrible batteries on traditional metrics, but on the metrics that are needed for grid scale storage, they might look okay. So I'm going to steal a little bit more time just to tell you about a recent effort that looked at real batteries that people care about that don't have horrible metrics or redefined metrics, and a way of looking at a closed reactor to think about the way all batteries work. And there was a tweet last winter that put the problem with state estimation in batteries perfectly. I cannot say it better myself, so I'm just going to crib it. It said, I made it home from Manhattan to Queens with 1% on my phone, and now I feel like I finally understand the story of Hanukkah. Right? So why does that happen? Why does, when a battery gets old, the state estimator on our phone gets really bad? It's a nuisance in our phone. It's a real schlep in a car. So we thought about this problem, and it's a huge problem for all batteries, because if we have the fancy equipment, you've seen the IAC, and we can cut the battery open, I can say, well, yeah, that's why it died, but then I cut the battery open, you can't continue to use it. And putting electrons in and out is just not sufficient, because it's locally predictive, but globally over time, fairly poor. So as I said, we spent a lot of time trying to recharge a AA battery. A friend of mine remembered this, sent me a video from YouTube that we recreated, and it goes something like this. When you have a AA battery and you drop it and it's fresh, it won't bounce. But if it's fully discharged, it'll bounce quite a bit. And we said, oh, this is cute. And then we went a step further than the YouTube video and said, what happens if we look at the battery's coefficient of restitution as a function of depth of discharge, and it turns out that it's nonlinear. Right? So because it's nonlinear, we get to write a paper about it. And as we discovered what the points of nonlinearity were, it just happened that the point where it started to bounce, and I can explain this during the break, why the curve looks the way it does, but the point where it just started to bounce is the point where the cyclability begins to get bad. And then the point where it plateaus is where you can simply not recharge it anymore. So these critical points on the bounce diagram, for lack of a better word, were strongly indicative of why and where and when you can recharge a AA battery. So we thought about, this is a silly way of testing high-energy batteries. I just said that batteries that are high energy are inherently bombs, so dropping them is a stupid thing to do. So the question becomes what can we learn from this study that's generalizable? So there's been a lot of great work at Princeton on looking at the mechanics of batteries. Craig Arnold is a leader on looking at static stress and strain within structures. And the problem with mechanics in batteries is that all batteries, because their reactors are inherently mechanical, but the way we've been looking at the mechanics to date has tracked the chemistry. So we have to know what the chemistry is beforehand to come up with an adequate mechanical solution to test it, which is great for understanding what's happening in a cell, but it's not so great for looking, thinking about, what is a battery generally. So we asked ourselves, is there a global connection? And the answer is yes, and here's why. Two things have to happen in all batteries as a function of their operation. The density has to shift, and if it's a solid state material that's reacting, the elastic modulus will most likely change. And what measures these things perfectly? Acoustics. Right, so sound speed tracks both of these quantities. And sound speed, and I learned all about sound in like the last year. Sound speed, when you have different sound speeds between different materials, it works an awful lot like optical refraction and refraction. Some waves go through, some waves come back. And the hypothesis is that cycling will affect all behaviors. The punchline is that it works quite well. So this is a movie of a battery. This is a real battery, like a battery that's in a RC helicopter. And this is the way a sound wave changes as you charge and discharge this battery. And we have not tested a battery yet, so we discovered this a little over a year ago. We have not tested a battery yet that has not shown a unique fingerprint in both what its structure is, and geophysicists have known this forever, but also as it charges and discharges, it follows a certain pattern, and as it dies, the way it dies gives new acoustic signals. So this is a way of quickly determining, without taking apart the cell, what's happening. So we put together these heat maps of basically time of flight versus cycle time to see how the battery progresses, and we get these beautiful structures that we're now approaching to understand in two ways. We're doing physics-based modeling to see why the structures look the way they look, and then we're coming up with just basically physics-free models to do data analysis, say, if this battery sounds like this, where is it in space and time? So it works on prismatic batteries, it works on 18650s. You can use it to tell the difference between different brands of batteries. Take this with a grain of salt because we've just commercialized this. So two of my postdocs have already left to California to try to make a go of this through DOE's Cyclotron Road program, and Schwarjo is leaving shortly. And I should mention that this is just 6 months in on a new RPE Ideas Award. So we're thrilled that we've been able to get so much traction so quickly. So thanks for your time. I hope I've shown you that an honest assessment of the couplings and compromise in battery can inform good, if not good, then new designs to solve new problems. And if we really think about what a battery is, not just the materials, but what the whole thing is, we might have a new universal diagnostic. Thanks for your time.
Thank you, Dan. We have time for a few questions, and just a reminder, please state your name and affiliation when you ask questions. Thank you. Yes.
So with your acoustics that you just showed us, you have this nice pulse going through, and that's how you're solving your equations. But what pulses really do is they attenuate and they spread.
Yeah. So you're absolutely right. So the attenuation is not so bad, right? So the real question is, why do we see anything? Because the thickness of the layers, we're using a 2 megahertz signal. We don't have much attenuation. But the thickness of our layers is far smaller than what that wavelength should be at an order of magnitude. The fact that we see anything at all is surprising, and I don't understand sound well enough to explain the sub-wavelength effects. As we go to higher frequencies, so, we did photoacoustic emission, for example, the attenuation is enormous, but we have a wavelength of the sound that's much smaller than the layers within a battery. So we're now going from on order a few megahertz to about 100 megahertz to sort of see if we can balance attenuation versus layer resolution. So attenuation is not a problem. The problem we have now with this method is that we see a lot of convolution of the layers. And the fact that we get any signal at all based on the amount of convolution in the layers is just frankly amazing. The acoustic model I showed you predicts that, and we're trying to work to understand how we can do deconvolution of that. That's a very good question. I just showed you a horrible battery. There have to be some questions.
There, yeah.
I'm Claire White. I'm one of these joint faculty between Andlinger Centre and Civil and Environmental Engineering. I'm going to sit down now. So when I grew up, there was rechargeable batteries, right? So you'd plug them in and they'd recharge a bit and then they'd die over time. Can you comment on how those rechargeable batteries are different to what you're looking at?
Oh yeah, so I mean, like I said, all unhappy families are different in different ways. So those batteries, and I think I'm not that much older than you, Claire, those are nickel cadmium batteries. And that's a really interesting system, and I've been talking with Bob Williams and now Peter a little bit about this. The cadmium forms something that's called a memory on it. And it dies because nickel oxyhydroxide electrode is basically bulletproof. Nickel's too expensive. So if nickel was a lot cheaper, then half of my job would be gone. So the cadmium hydroxide forms a memory based on the protonation reaction. So it forms a stratified structure as you charge and discharge it. So if you didn't discharge it fully, it built up what we call the memory. And it's this funny thing because it's the only battery that really does this. So the first generation of rechargeable batteries that we used in daily life had this effect. And we've carried over the way we treat them to lithium ion, which are completely different. So with nickel cad, you weren't supposed to partially use them. You're supposed to pull them all the way down and break them up. Lithium ions completely the other way. You want to use them minimally. So that's why those died. So it goes back to the point that understanding the failure mechanism. So it's really that's a balance between passivation and corrosion. So it passivates, and then there's local corrosion, which allows some of the material to be reactivated, but it stores in a layer some of the passivated material.
Bob Harris, retired. The bubbles that we saw in your video, was that bromine?
Hydrogen.
Hydrogen.
Yeah. So I'm sorry for glossing over. There are a lot of side reactions. The point is that every side reaction we can account for. So within a lithium-ion battery, you cannot have anything that looks remotely like that. If the lithium is lost in inventory, cycle life goes down. The hydrogen that forms, even though it's quite violent, is a relatively small fraction of the current pass. So we still have Coulombic efficiency, even in that case on the order of 88%. We designed the cells, and this was a surprising thing when we're working with Bruce Kale on this, to understand that it turns out that cheaper carbons are okay because cheaper carbons have a little bit of metal something on them, which recatalyzes the bromine and hydrogen recombination. So the hydrogen, if we can capture it, will just eventually recombine with the bromine that does escape into the headspace. So now we're trying to design a reactor that can speed up that process a bit. But we were really worried that we would lose too much hydrogen and we would get very few cycles. And we've run these cells for over a year with minimal electrolyte loss. Yeah, it's a very good question. Thank you. Microphone.
Can you compare, on whatever metrics you think are important, your carbon HBr bromine battery?
Sure. So
other flow batteries.
Yeah. So if I showed you a small cell, if we can, right? If you took that cell and multiplied what we had there, you would have a cost that, on a reactor basis, is about to a fourth of what a flow battery is. But it has much worse power density. So flow batteries are really tough because they decouple energy and power. And no one tells you how much the tank costs and the plumbing costs. They're hard numbers to get. What I've seen final installs for flow batteries is on the order of $400 to $500 per kilowatt hour in an optimistic scenario, with all the stuff, which is still pretty high. What I showed there was about 120 per kilowatt hour with very little optimization. We have designs in lab. That's at 75% round-trip efficiency. When we go to 60% round-trip efficiency, the cost is $90 per kilowatt hour. So now we're trying to engineer that $90 per kilowatt hour. And that's inclusive. That's every bit of the cell. It's not just the active materials, but it includes the glass and the construction and the water. The next step is to sort of do $90 per kilowatt hour basis at 75%. And we have indication with minimal complexing, and this is really the bet, that we can get it down to 50 at 75%. So if you can live with a round-trip efficiency over a day or two of 75% at $50 per kilowatt hour, I think there's a path. That's sort of the engineering goal. Flow batteries, the reactors, it's hard to say. It's hard to say if the reactors will how much cheaper they can get. I don't know.
What is their typical round-trip efficiency right now, any commercial flow battery?
75–80%.
Okay.
Depending on how hard, but at much higher power density. So at low power densities, they're not much better. It's quite complicated because of crossover problems. The other thing about flow batteries, though, is that the membranes eventually degrade. Things break. So I still work on flow batteries and flow assist batteries, but all of that extra balance of plant, they say, oh, look, that's an O&M cost. It's hard to have a battery the size of a turbine. It's easy to sort of point to a turbine. Mike Mueller and I talk about this all the time. It's easy to point to a really big turbine and say, okay, that's easy to operate and maintain, because someone can walk into the turbine and clean it off. You're never going to have a single battery that's big enough that someone can walk into and draining it out. So if you have these designs, replacing the membranes, you say, okay, well, that's a maintainable thing, but it's really hard to get into. So thanks for bringing this up, Emily. Part of the design here was to get rid of anything that could break. There's no membrane.
All right. One last question, comment. We all hope for these massive batteries to integrate with the grid, with renewables. Where are we? What are the challenges?
Yeah, so if you asked me when I came here, I'd be like, we're really far off. These new lithium-ion prices out of, and there's a lot of talk over beers about where they came from, whether or not they were coming, so Elon Musk threw down a gauntlet and said, they've got to be a lot cheaper, and I'm going to make them cheaper. And people, including myself, said, haha, that's like they're already a commodity. How are you going to make them substantially cheaper? And he said, I'm only going to make them 20% cheaper. And we said, okay, well, yeah, you can get there. And then all of a sudden, LG said, within 6 months, they started selling batteries to GM at 40% cheaper. Not 5 years down the road, but now. So now you can buy, right? And whether or not this is a real price or a forward price or somewhere in between is unclear. But you can get, on a cell basis, $145 per kilowatt hour. And if you can cycle that 5,000 times, and you might be able to, then you're within spitting distance of that green bar with lithium-ion. So for congested markets like New York, lithium-ion looks really good. And I would not have said this 3 years ago. It's really amazing what's happened in terms of costs. I hope these costs are real.
Well, thank you, everybody. So we